Good day. Welcome to yet another session of E-Pathshala PG version. The topic to which this is being added is basically services in a high-rise building. On a cursory look, one would wonder, what does vibration analysis have to do with a high-rise building? But a calculated thinking would lead one to realize that it is one of the most important topics that is required, and it is the air conditioning man who is handling it today for you, because basically air conditioning equipment is the equipment in a high rise building which works the longest hours and practically is on throughout the day. Now, every time the building is occupied, this mechanical equipment which runs tends to transmit a certain amount of energy. Its inefficiency, it's basically into the form of vibration which is into the structure. Now, this can definitely be at certain points of energy levels where it can be objectionable. At certain levels it becomes tolerable, but ideally it should not be perceptible. Regardless of what one might do, even if you buy some of the best equipment, over a period of time you will find that the equipment has undergone some amount of aging. Some of the bearings have gone, the maintenance crew has not been able to smart enough replace, some of the belts have become loose and they tend to vibrate. Now, these vibration definitely cannot be attenuated on a day-to-day basis. So, it is up to a designer to be able to allow for a certain amount of attenuation and control on these by putting in proper equipment for these kind of devices. Air conditioning equipment, as I mentioned, is basically a heat pump. The intention of giving this kind of definition is that the moment you call it a pump, you visualize that it is not something which is like a black box. You realize that it is a mechanical equipment, and you realize that if it is a mechanical equipment, it can vibrate. Basically, any vibrating equipment generally would imply that it is less efficient than non-vibrating equipment, because any vibration again consumes energy which comes from the power you have fed in. For instance, if you have a very good fan, if it does not vibrate, you will find that it consumes much less energy. Take the same fan, remove the bearings and put in a normal worn out bearing on this, you will find that the HP climbs up, you lose money on power and the fan starts vibrating. So, in other words, it is nicer to be able to stop the pollution of vibration at the source. That means, if you realize that there are certain things which can be attended like bearings, these things should be replaced immediately. What we will now see is, despite all that attention, if there is a certain amount of transmission, what is it that one can do? What is it that one can do if you have vibration or you are planning to allow for vibration? The moment that you start to be able to allow vibration to come to the device on which you are trying to protect, let us say a high rise building, it will become necessary to be able to know a little about vibration. It is very necessary to realize that vibration is an extremely complex parameter, and if its analysis is done in a very systematic manner, sometimes it might take not a few weeks but a few months. It is like in a body, if surgery were to be classified as complex, it is always the neurosurgeon who says my part of the body is the one that requires the maximum attention, and a neurosurgeon sometimes counts his surgery in terms of days, not hours. Like that, vibration analysis in terms of any other analysis on a building can be termed as an extremely complex parameter, running into half a dozen Fourier series, running into half a dozen assumptions, which unfortunately or fortunately sometimes do not get you the results you are looking for. So, with all the calculations and all, ultimately it is a good astute designer who not only is good at his calculation and analysis, but is also good at practical work to be able to give you a system and a device and a building which does not have any discomfort due to vibration. Let me take you into an aside on the subject of vibration. I am sure people who have followed aircraft engineering, people who have followed the way aircraft are made, they will remember that there was a very serious problem a couple of decades back. There was an aircraft which was very popular. It was the Comet, which had suddenly developed to a cursory inspection some cracks on a couple of aircraft on the wings. A serious analysis or a serious observation led to the fact that these vibrations were occurring practically on all the aircraft which had come out of that particular time frame from the machine. The DGCA was very fast in grounding all the aircraft, and they started an analysis to find out why these cracks had developed. After a few weeks, it was found that the engine vibration had transmitted itself on the frame of the wing, and the wings had developed these cracks. The whole fleet was grounded, no solutions were available, and the company which used to make these aircraft, de Havilland, had to close down because they could not, they had put all their eggs in one basket. This was the only aircraft they were making, and when this was grounded and they did not have a solution to put it back, the company had to be closed. So, this is at one end to say how vibration can become such a serious issue, and it can become issue on air conditioning equipment, creating vibration in a building which can lead to, in a small building, people having to leave the building unoccupied. A similar analysis one might look around and say was on a flight of NASA. Like I said, if somebody could really do an analysis and yet not find a solution, this was one of the stark examples where a flight was about to take up, a final countdown had started, but with the parameters that are connected to the control panels, it was observed that in the final few hours of countdown, certain components in the rocket had started vibrating. The same engineer who had done all the vibration analysis was available. He went down, started looking at the main control panel to see what could be the reason. I can assure you that when he went on board, he did not carry his computer to do a Fourier analysis. He did not carry anything. It was purely his hands, his own senses, and his own common sense which had to solve the problem. He suddenly found that the entire panel was vibrating. The panel was resting on the craft with some distant separation by, you might call, legs. It just occurred to him that this would the legs were not able to absorb the vibration. He took out his pencil eraser, which fortunately was in the shape of a car, which has two wheels at the bottom and a flat surface on the top. He pushed it into that gap, and the vibration stopped. He solved the problem, came out, and NASA was good enough to take a risk on what he had done because they had virtually little choice, and the plane took off. And I have really, after that, not followed up. Maybe the car is still circling over our heads. Now, let us get on to the subject. What is it that this toy car did? When the power panel was sitting on the device that it was going to control, it had inherently developed a certain amount of static deflection. In other words, the panel, when it was empty, had a particular deflection, and when it was loaded, it had deflected down by a few millimeters. Now, that is called static deflection. The moment you have a certain amount of static deflection, it plays on a parameter called the natural frequency of that particular item. Now, the disturbing frequency, which we will see later, the disturbing frequency and natural frequency cannot coincide. So, by putting a device like a rubber toy, one altered the static deflection of the media and change the natural frequency of the structure. Suffice it to say that even a building 10 story, 20 story, 50 story has a natural frequency. What disturbs this natural frequency must be a disturbing frequency and a natural frequency far apart from one another. Otherwise, if they are very close, they will suffer resonance and the building can collapse. This rubber toy played around with the static deflection, developed a new natural frequency and attenuated the vibration. Now, what is disturbing frequency? The disturbing frequency, as the name implies, is the frequency of the force which is causing the vibration. Now, coming back to why, we are not looking at de Havilland making a comet aircraft, we are not looking at Dr. Robin trying to solve the comet engineering issue. We are looking at very simple staid commercial air conditioning equipment sitting in a high rise building. Yes, it causes vibration. We are looking at how to be able to analyze this and make sure that it vibrates but does not get transmitted on to the occupant of the building. The disturbing frequency that one sees is basically developed from an air conditioner. Maybe it can be from a DG set, maybe it can be from a transformer, but suffice it to say that as an air conditioning topic, we will stick to an air conditioning, which can be covers and can be extended to things like a DG set, a diesel generator set, maybe a transformer also, which is though static tends to vibrate at a very high frequency when its plates are a little loose. Now, coming to an air conditioner, what are the equipment that move inside? Let us say you have a fan in an air conditioner. You cannot do an air conditioner without a fan. So, there is a fan. Its blades are there, its motor is there, its drive shaft is there, its fan blade is there. Then apart from this, you have the more power consuming equipment like compressor. Now, all these move, vibrate, roll about and cause definitely vibration on the equipment. The intention is that you cannot do anything on the equipment which you have bought. Basically, it is a manufacturer's. At best, you can buy the best equipment, but suffice it to say that even the best equipment does vibrate. So, the exercise that you are looking at is to say good equipment, vibration not to be transmitted around to my structure. Now, at that point of time, you look into the disturbing frequency of the material. And the disturbing frequency, considering that the multitude of equipment that you have on hand will always be classified as the lowest frequency. That is, for instance, now you have a fan, its lowest frequency will be its wheel. Now, a fan wheel may have 10 blades. So, the frequency of the blade will be 10 times the frequency of the wheel. So, take the lowest frequency as the one that is going to bother you. Now, this is available. You have to make sure that this does not coincide with the natural frequency of the place you are working with. So, basically what will be done is you try to put the natural frequency and the disturbing frequency far apart from one another. How do we do this? Like we saw in the earlier two examples, basically you play around with the natural frequency, which, for instance, as I said earlier, with the equipment one has very little choice except to buy the best. Having bought the best, we know that it has a certain amount of vibration. We want to make sure that it does not impact the comfort of the people who occupy the building, which is your topic of interest. So, at that point of time, you play around with the natural frequency of the structure. The natural frequency of the structure can be very simply classified, forgetting about all the analysis which a doctorate in engineering will be required to do. Is a very simple formula to say natural frequency is equal to 1 by the square root of d, where d is the static deflection. This d and this d are coincidentally the same. It is my mistake to say that this is small d and this big D, but the intention is that both are same. So, in other words, you have a natural frequency of the structure which is 1 by square root of d. This has to be kept away from the disturbing frequency, for which there are very simple nomograms, there are very simple curves which one can play around with. So, having developed these two topics, natural frequency and disturbing frequency, one plays around with a little bit of calculation, again with the help of a very simple curve. These are curves which are available in any textbook, any simple book, any simple standards book which shows you how to transmit vibration to a structure without actually vibrating the structure. In this, one has a choice to select a high level of control or a low level of control. For instance, now we are doing something, let us say you are putting an AC equipment over a garage. There is no point in trying to work at 97%, you can come down to perhaps 93%, 94%. These are the curves which are available and they are plotted against static deflection on the y axis and vibrating frequency on the x axis. Now, vibrating frequency is known by the lowest RPM of the AC equipment. What is required is to plot that point here and go up to the curve you have selected. Let us say it is not a garage, you are working on an office building where you want very good attenuation, 97%, even better. So, from here, from the disturbing frequency, one climbs up to the natural frequency level, and from here he goes across to establish what is going to be the static deflection required. Now, based on this static deflection, one has to buy vibration isolator which will go under the equipment. This is that rubber toy which our Superman put under the power panel in the NASA aircraft. For example, if you were having access to those curves, you will find that for a very low level of isolation, something like 90%, if the disturbing frequency were 700 cycles, you will need a static deflector which deflects by 150 mm, close to 6 inches. Likewise, if on the same equipment you did not have slow speed equipment, you had high speed equipment running at 3000 cycles, then instead of 150 mm you will require only 0.15 mm. So, this establishes the kind of importance the disturbing frequency has. If the disturbance frequency is low, you will need a high static deflection. If it is high, you need very small deflectors. How do these static deflectors look? Most of them basically are rubber and shear. You will find that this is an equipment which is mounted on like this. Here it is completely mounted. Here are the two deflectors. You have basically a metal, another metal on top, and this is held together by two pieces of rubber. So, in other words, when this is loaded at this point, it tends to transmit the load through these two rubber devices, and the rubber is not loaded in compression. If you will notice, it is loaded in shear. This is the load, this is the equipment, this is the condenser fan, this is the motor. You isolate which is the lowest RPM, select this for whatever it is required, and this is the amount of deflection which was when it was undeflected. So, when there was no load on top, you will notice that it was deflecting by 150 mm. When it is loaded, it has now come down to 130 mm, easily measurable. A simple scale is good enough. So, in other words, between these two there is a static deflection of undeflected mount was so much, deflected mount is so much, the static deflection is 20 mm. Now, this is the only single parameter that will go into our earlier equation of Fn is equal to 1 by square root of d, and we will immediately develop a requirement for the AV mount, anti-vibration mount. In other words, what is required is basically a control on the deflection in relation to the RPM of the equipment that you are bringing. That is what it is in common parlance. Now, what I showed you was a rubber and shear device. These mounts, AV mounts meaning anti-vibration mounts, can be available in various forms. They are available as padded material, they are available as rubber and shear, they are available as springs. Now, if you just look at the geometry, if you just look at the physical parameters of these three, you will find that this device is the one that tends to give you the largest vibration. It is what you see in a lorry, it is what you see under your car. The spring may be in the form of a leaf spring, it may be in form of a coil spring, but those are the devices which give you the maximum amount of vibration. If you just look at a lorry underside, you will find that leaf springs tend to vibrate tend to deflect upon a particular disturbance as much as 150, 180 mm also. This gives you the insight of, for instance, a padded material. This is something that what you would use for very small deflections, meaning that 0.15 which we saw in the earlier example, meaning high frequency. So, in other words, if you have a high frequency equipment to be attenuated, which is running at a very big speed, okay, it's very nice to be able to just put a cork sheet under it, which is a pad. You could put a rubber sheet, which is again a pad, or you could put something which has cork and rubber combined, so it is called a combination of the two. Like for instance, you have a kitchen, you keep your mixie there, at its lowest frequency it is a quite high thing. If you want to attenuate that noise from coming onto the table, all that you need is a small pad underneath which will be able to deflect by that frequency. If the lowest RPM there is 700, 800, then you will need a pad which is big. But in most of these mixies and all, the frequencies are very high. So, it is sufficient to be able to have a soft pad which will deflect by maybe say 6 mm, 8 mm, and you get a good attenuation, your table will stop vibrating. The next item which we saw from the type of mounts you get is rubber and shear. This is what we saw in the first example. Basically, you have a device which is separated from a moving and the static. So, in other words, this is the moving device, this is the static device. The moving device and the static device are connected by rubber, which will deflect. But please notice that this is never rubber in compression. For instance, now if this were rubber here and this were the guiding force and this were the mount, you will find that it's rubber in compression. That very rarely gives you the kind of attenuation that would be akin to padded material. To get larger degree of static deflection, one goes in for this kind of rubber and shear mount. In a foundation, it can take this shape. If it is for a ceiling suspended pipeline to be, it can take this shape. In other words, you can imagine this is a ceiling where these two holes permit you to screw in this rod onto the top. The rod is covered with rubber, which again supports a small hanger at the bottom, and this is the. So, you notice that the vibration equipment is not directly connected to the anchoring equipment. The only connection is through a tedious path. That means it transmits its vibration here, goes here, and through the rubber it gets transmitted to the support equipment. So, this rubber is not rubber under compression, this is rubber under shear, because this is pulling it down, this is resisting it up. So, this rubber is in shear. Now, rubber and shear can give you this kind of static deflections, 20 mm, 25 mm. As I mentioned in my audio first, basically springs are devices which give you the largest deflection. They are useful for supporting fans which generally run at low RPM. So, if you have a fan, if you have a kitchen exhaust fan from a basement restaurant sitting on the roof and the flat below or the office below is tending to make noise, all you have got to do is on the base support it on springs which are flexible enough to be able to give you the static deflection of the disturbing frequency. For instance, this might be, let us say, 1500 RPM motor, this might be a 700 RPM fan. The RPM is reduced due to the belt drive. You use 700 RPM as the disturbing frequency, design your spring on that, buy it, you can buy your spring saying that this is my total load, this is my deflection required, I need sprig springs, and put in the equipment. After that, there is absolutely no vibration. As I mentioned, all the three types of common vibration mounts we saw, they are basically material which allow your equipment to float off the structure and give you the static deflection to be able to avoid transmission of vibration. Now, any floating equipment has the parameter that it is not rigidly connected to the equipment or to the structure. In other words, supposing there were a thing like an earthquake, or supposing there were maybe a disturbing frequency on the structure, the floating material could collapse and the equipment could fall and cause you problems. So, such type of attention requires that whatever was floating should have a stay. That means it should be allowed to float up to a point, and after that it should be able to restrain. Now, those are called seismic restraints. These are purely add-ons to the devices that we saw earlier. In earthquake prone areas, it is very necessary to be able to override anti-vibration mount with a seismic restraint. As the word restraint implies, after that point the equipment will not stop the vibration, but it will stop itself from collapse. So, after the earthquake is cleared, you can perhaps replace the AV mount and you are back to square one without any problem. Now, this is a feature where you will see the AV mount, these red items are the springs. Now, this is the seismic constraint. That means, should there be a problem, should this move, you will find that if this collapses or the movement is, see, these were designed for a moving frequency of equipment on the fan. Now, you are getting a low frequency from seismic, let us say earthquake. At that point of time, for the low cycles, these restraints will take over. This housing will act like a restraint. If the spring moves or collapses, this will sit here and the distance will be perhaps maybe few mm. So, nothing will happen to the equipment, nothing will happen. After the disturbance of the seismic problem is solved, one has to just jack up this equipment, replace the springs, and you are back in business. Now, this, as I mentioned earlier, is a mount which is basically used for high deflections. Not that it cannot be used for small deflections, but it is a little expensive and people tend to use it only appropriately where high deflections are called for and it is kept invariably exposed to weather outside. The housing tends to protect the spring, which of course has its own cadmium protection and all that, but apart from it the device by itself is weatherproof, sturdy, and protects the equipment for the life of the equipment onto its own mount. Apart from it, as mentioned earlier, should there be a seismic disturbance, like let us say a mild earthquake, it will just topple the equipment onto a device which is more powerful than the spring, better grounded, and it gets immediately flowed onto a device which has shorted what was earlier the floating equipment. In other words, the spring gets shorted at the time when you have a disturbance which it is not planned for. A seismic disturbance is basically a low frequency disturbance. It is not only a low disturbance frequency, depending on the type of seismic problem you envisage, you might have a movement lateral, you might have a longitudinal movement. Now, all these tend to get restrained by the housing that you see in this picture. Now, these kind of housings which are shown for a spring can be similarly devised for things like rubber and shear. Padded material, it might be a little difficult to be able to put in a seismic restraint, but if you look at the geometry of a padded material, you will find that perhaps you do not need too much of protection, because the static deflection is very small. So, the float is very small. So, in the case of a seismic deflection, one might find a very little amount of disturbance that this can take. A simple device, a simple way of building in a seismic protection on a padded material is to drill a 1-inch diameter hole in the pad and put a 1/2 inch diameter nut and bolt on the device. So, in normal practice, in normal working, you will find that this 1/2 inch bolt does not touch the hole at all. But should there be a seismic problem, this bolt can move the remainder of the annular gap around the big hole and still be able to arrest the equipment in place. So, that would be a very simple way of adding a seismic protection onto a padded material. For the rubber and shear, one would have to look at some extra devices like you see the housing on the spring. You will need a shorting device which will be able to take over. In the normal mode, it will not touch the moving device, but in the seismic defect, it will be able to go and contact the equipment and take over and short the floating device, so that it is in place. I mean, it is in place. Such a housing would presuppose that before you recommission the equipment after the seismic disturbance is cleared, that you remove the mount, clear it for what it has suffered, and then put it back or put in a new mount. New mounts cost barely maybe 0.001% of the equipment cost and are available on call and can be put in without any problem. Thank you.